Okay, so let's begin. So I was talking about spectral clustering as another kind of clustering algorithm. So it's an alternative to k-means, right? So we have looked at k-means, and you have done a few problems associated with k-means. And one of the biggest problems with issues with k-means is that it tries to find these clusters which are sort of spherical in nature, right? Because if you try to understand the k-means clustering algorithm, what it tries to do is, for every centroid, it tries to find points that are closest to it, right, using a Euclidean distance or any distance norm. But the idea is that it tries to sort of draw this sphere in whatever dimensional space you have, and tries to find points that are within those spheres. So as an effect of that, the clusters that come out from k-means have sort of this globular nature. Okay, so if in your data the natural clusters look like those, then k-means will work very well. But if the clusters are of slightly different quality, then k-means fails miserably. Okay, so just to give you that, just to show you that issue, I think I showed it last time as well, but let's go back here. So if you look at data which looks like, let's say, this, right? So this is our data, okay? So this is two-dimensional data, and the natural clusters, or the clusters that you do want to identify, are these two concentric circles, right? But when you run k-means on this, even when you tell k-means that you're looking for two clusters, right? So even in that case, what k-means does is it tries to find these, I don't know if you can see yellow and red, right? So these are the two clusters it finds. And that is kind of an issue with k-means, because it tries to partition data so that they sort of become these balls. But because the natural clusters are not looking like balls, which means that k-means kind of fails in that sense, right? So then so that kind of leads us to the question that, are there any algorithms which could identify clusters correctly in this setting, right? So one of those is what we call spectral clustering, right? So in spectral clustering, the idea is that you have some data, you first convert it into a graph, okay? And last time I showed you how to exactly do that, right? So what you do is, you take your data points, you measure distances between them, and then you create a graph in which each point becomes a node, and then an edge, you connect two nodes if they are very close. Okay, so of course that very is subjective. So typically you put some kind of threshold. So you say, okay, let me put an edge between every node and its closest neighbor. That would be one example. Or you can say, let me put an edge between one node and two of its closest neighbors, right? Where the closest comes from the fact that you have a distance metric, right? So that is the idea. So here, sort of mathematically or algorithmically, this is how you do it. So you have some data x, which has n data points. You create a similarity matrix, which is n cross n, in which each entry is essentially the similarity between those two objects, right? Now this could be similarity or distance, whatever, right? And then from that, you construct a graph, right? So I'm hoping you're familiar with graphs. So every graph has two things. One is a set of nodes, and then second is the edges that connect these nodes, right? And sometimes you have weights on these edges as well, and sometimes they are just 0 and 1, right? Where 0 indicates that there is no edge, and 1 indicates there is an edge, right? So that matrix is also known as the adjacency matrix of the graph, right? So you can construct an adjacency matrix from the similarity function like this. After that, what we do is, now we work with graphs, okay? Now our task of finding clusters translates to finding communities in this graph. Now what is a community? So if you think of, well, community kind of comes from more of a, if you look at a social network graph, but in general, if you have a graph, right, as I said, every graph has nodes, and then there are some edges. Right, let's say this is the graph, right, and there are no edges between these two. So the task of clustering now becomes trying to identify these two components. So we call these disconnected components, right? So a component is essentially a subset of a graph in which there is a path between every pair of nodes, right? Whereas two disconnected components will have no connections across these components. So now your task of clustering, so clustering of the actual data X now becomes equivalent to finding components in G, where G is, you get G from X by doing that similarity function and so on, right? Now it could also happen that your graph might not have these disconnected components. Maybe there is an edge like this. Even then, what you're interested in is to identify these two components anyway, because these components kind of seem like they are two disconnected components, right? So that is the idea, okay? So now we will see a method through which we can identify these components. Any questions so far? All right. Okay, so essentially what happens when you convert your data into a graph is that your task of finding k clusters, right, which was your original task, now becomes equivalent to finding k cuts in the graph. So cut essentially means you remove an edge and then you get these two nice components, right? So that is a cut. So you want to find k cuts, and these cuts need to follow some property. So intuitively, the cut should be such that all the cuts, I mean, when I say a cut, it is a subset of nodes. They need to be heavily connected with each other, and there should not be any connections across the nodes, right? So for example, here, by removing this edge, you get these two cuts. So these are good cuts because there are edges between these, within this sort of one cut, edges within this, and very few edges across, right? However, if you say I'm going to use this as a cut, then it's not a very good cut, because then there are edges. So let's say you remove these two edges, right? Then this versus this, so it's not a very good cut in that sense, right? So the objective function becomes slightly different. So instead of trying to minimize, so in k-means we have this objective function. Here it translates to slightly different. You're trying to identify cuts such that edges across cuts are minimized. So that this is just a mathematical way of saying that, all right? So one issue that I pointed out last time was that if you just have this as your definition, then you could always get a very trivial solution, which is you take one node in one cut and everything else in another cut, right? And that would maximize this property. So, but you don't want that. That's too trivial a solution. So you pose this normalized min cut problem in which you're trying to find cuts which are not only sort of within themselves, but they're also big. So they need to be big enough, as well as they need to have very few edges across the nodes, all right? And everywhere, I do talk about weights as well. So remember, see, edges can also have weights on them. So you can easily generalize this property of normalized min cut or min cut, assuming that these are also weights, right? So you want to split your graph into parts such that all the edges within one part have very high weight, and there are very low weight edges going out, or no edges going out at all, right? Is that sort of clear? So of course, now what we saw last time was that this, posing it like this, makes it an NP-hard problem, right? And you can see that, I'm not going to go into that too much, but essentially it is equivalent to solving a 0-1 knapsack problem, which in computer science is a well-known NP-complete problem, right? So how do we still find these cuts? So now our problem becomes slightly different. Given a graph, how do we identify these cuts, right? Knowing that if you have original data, you can convert it into a graph, so that now you could use that as a clustering method, right? So one technique is if you do eigenvector analysis of the data, all right? So that is why this method is also known as spectral clustering. So in math, right, if you have a matrix, you're doing its eigenvector analysis, you're essentially trying to understand this. Those are known as spectral methods, right? So that's why the name of this technique is spectral clustering, all right? So let's look at how it works. So to understand that, one thing that we need to understand is a notion of something called a Laplacian. All right, so let's look at that. So let's first look at a graph. So let's say we have a graph. All right, so I'm using this very nice Python library called NetworkX, which you can use to analyze graphs. So it has a lot of interesting, lot of useful methods inside to study properties of graphs. You can also use it to generate sample graphs and so on. So for example, here I'm creating a graph. You don't have to worry about what this graph is, but essentially it's going to be a graph which looks like this. All right. So let's say this is the graph that I have sort of generated. So it has 10 nodes numbered from 0, 1, 2, 3, and so on through 9, right? So this is the notion of a graph, and this is the adjacency matrix of the graph, all right? So if you see, it is a 10 cross 10 matrix, and it has a 1 wherever there is an edge. So for example, node 0 is connected to node 5, 0 is connected to 5, so there is a 1 there, and so there'll be some ones, there'll be some zeros, right? In general, you could also have weights on these edges, which means that these numbers would not just be 0 and 1, they could be any real number, which will denote the weight. But here, just for simplicity, we are assuming that this is sort of just a unweighted graph. All right, so this is our graph. This is the adjacency matrix. All right, then there is a notion of something called Laplacian of an adjacency matrix of a graph. So what is a Laplacian? So first we construct this matrix, which is, I'm just going to call it a degree matrix. Essentially this is a diagonal matrix, all right, such that all the non-diagonal elements are 0. The diagonal entries are just the degree of that node. Okay, so a degree of a node is just the number of edges that are connected. So for 1, its degree will be 1, 2, 3, 4, 5, because it is connected to 5 nodes, 5 other nodes. Degree of 7 would be 1, 2, 3, 4, 5, and so on, right? So okay, I need to run it again. Right. It looks very strange, right? It's, I'm sorry. Yeah, I'm looking at 0. So 0 has a degree 4. You're right, and so on. So this is a sort of a diagonal matrix. We call it D. It doesn't have any name, but the idea is that this matrix has zeros on the off diagonals and the degree of that corresponding node on the diagonal, right? So that is something that you can easily draw. And then if you compute this value, this is D minus W. So the degree matrix minus the adjacency matrix, right? This is what we call the Laplacian, all right? So Laplacian is nothing but D minus W. It's just something that you can compute, all right? And it would look like something, right? But essentially the idea is that the Laplacian is D minus W, and it has some interesting properties. So we are going to study that, all right? So the main result of a Laplacian is that if you have a Laplacian matrix and if you do its eigenvector analysis, right, then it is guaranteed to have at least one eigenvalue which is 0, all right, and one eigenvector which is all ones or all equal value, because if it's something, you can always transfer that constant out and it becomes all ones, right? But the main point is that if I have a Laplacian L, which is D minus W, will have at least one eigenvalue which is 0 and at least one eigenvector which is all 1. So I'm going to write it as 1, like a bold 1. Basically this is a vector. This is a n cross 1 vector with all 1s on it, right? Which essentially means that so what does it mean that an eigenvalue is 0 and eigenvector is 1? Which means that L times this 1, right, is equal to 1 times 0, right? Because if you remember, eigenvector analysis essentially means that if you have something like this, then Ax equal to lambda x, right? So if you have vector, then the solution for this would be all eigenvectors of A, right? So that is a so the main result is that there will be at least one eigenvalue which is 0 and one eigenvector which is all 1, and that is easy to see because remember, now what does it mean that if you take any matrix, right, and if you multiply it with all ones, right, what does that mean? It means that so let's say this is n cross n and this is n cross 1, right? So the output of this is going to be a n cross 1 vector, right? And every entry here is going to be what? Every entry here is essentially this row multiplied with this whole column, which is, and sum it up, which essentially means it's a sum of all the rows, right? So in you know, whenever you're sort of doing some calculations with matrices, if you want to compute the row sums, all you do is you take your matrix and you multiply it with a vector of ones, right? So this is essentially a sum of first row of L, right? Now let's look at this. So this is the first row of L, which means that this is essentially a sum of the first row of D minus W, right? Now, so the first entry is the sum of first row of L, right? Which essentially means that it is the sum of first row of D minus L or D minus W, right? So now remember that this is what? This is basically L was D minus W, right? So this is D and this is W, right? And D had this is the degree of first node, right? And everything else is 0 here, right? So essentially you are subtracting the degree with the sum of this row, and this row is nothing but the degree of this node, right? So which means that this value will essentially be 0 because this is summing up all the values in W, which is the degree of the of this node, which essentially is the first diagonal entry in this, right? So it's easy. So that gives you 0, which essentially means that this time this is a vector of zeros, right? So the logic is that L times 1 can be written as a 0 vector, right? Which can be written as a vector 1 times value 0, which essentially means that if you do the eigenvector analysis of L, you will get one eigenvalue which is 0 and one eigenvector which is 1, or it could be any constant because it could be, you know, all 0.3s times 1 over 3 times 0, because that doesn't matter, it gets absorbed in 0 anyway, right? So that is the point, right? So you can see that in this simple graph as well. So if I do the eigenvector analysis of this matrix, these are the eigenvectors, so these are the eigenvalues. So you see that there is this which is close to 0, that there is some numeric precision here, but this is the 0th eigenvalue. So you take any eigenvector, any Laplacian, if you do its eigenvector analysis, you'll get at least one eigenvalue which is 0, and the corresponding eigenvector will be all constant. So this is a plot of all the eigenvalues, right? Yeah. So these are all the eigenvalues. So you see one of them is 0, and then the corresponding eigenvector is all constant. It is not all ones, but it is something, but it is all constant, which means it's kind of essentially 1, right? So that is the property of a Laplacian. A Laplacian will always have at least one eigenvalue, which is 0. But where does it get us, right? So why are we discussing that? The next interesting property of a Laplacian is that if your graph has disconnected components, right? So let's say your graph has two if your graph has two disconnected components, let's say there's no edge like that, right? So let's say your graph looks like this. There are 4 nodes here or 5 nodes like this, and then there's another component here. Then if you compute, let's say this is my graph G, if you do the Laplacian, do the eigenvector analysis, then it will have 2 eigenvalues which are 0. All right, there will be 2 0 eigenvalues, and then you can just follow the logic we followed here to prove this, right? And this thing will hold again, Okay, because the idea behind having a disconnected components is that essentially in your W matrix, right, the adjacency matrix, you will have two blocks. There will be some ones, some zeros here, which which correspond to this. And this would be another, and then there will be no edges. There will be all zeros here because there is no edge across these blocks of nodes, right? So you can follow the same sort of logic, and you can prove that the Laplacian of this graph, right, L of G, will have two eigenvalues which are 0. Okay, which essentially gives you a very easy way of identifying disconnected components in a graph. So all you do is, let's say here I have created a graph manually, right? So I've created graphs with two components. One is this, one is this. If I do the whole Laplacian eigenvector analysis of this, you will see that this first plot, this is the plot of all eigenvalues, right? You see that there are two zero eigenvalues, right? Which essentially is what I was trying to say. And if you look at the corresponding eigenvectors, what you will see is that one of the eigenvectors will have one, like all zeros here, all zeros here, which essentially corresponds to this, or this one, this eigenvector, right? 7, 6, 7, 8, 9. And the second eigenvector, for which the eigenvalue is 0, will correspond to all zeros for the other component, right? So what you can do now is easily, if I give you a graph and I give you its eigenvector decomposition, you can study it, right? And then you can identify which are the two disconnected components by looking by. So what you do is you first do the eigenvector analysis of the Laplacian matrix, right? So let me give you this algorithm. So finding disconnected components. Right. So you're given a graph G, right, which means that you're given its adjacency matrix. So step 1 is you compute L. L is d minus W. Step 2 is you do the eigenvector decomposition of L. Right. So these are the eigenvectors and these are the eigenvalues. Step 3, for each j such that V of j equal to 0, which means you're trying to find the eigenvalues as 0, right? You take E of j, which is the eigenvector, corresponding eigenvector. So this will be a vector, right? This is an n cross 1 vector, and identify then you find a set of i's such that Eij is not equal to 0. So this will be component J. So if you follow this algorithm, right, what will happen is, first you will do the eigenvector analysis, then you will look at every non-zero element, right, and every zeroth element of this eigenvalue, all the eigenvalues. Then for that eigenvalue, you will look at its eigenvector, and then you will identify the points where it is non-zero. So all those points will belong to one component. So for example, if I go back here, right, so essentially these are all the eigenvalues. I've just plotted them. So these two are the two eigenvalues which are 0. So I will look at the corresponding eigenvector. So this one is corresponding to this eigenvalue. So here I will look at all those nodes for which this eigenvector has non-zero values, which will be these first 5 nodes, 0, 1, 2, 3, and 4. So these will form one component, and then I'll look at the other one, and other one, these are the ones that are non-zero, so these will form the other component. All right? Any questions so far? All right. Yes. The algorithm? The process? All right. So if I give you a graph G, okay, and of course here you can see it, but let's say I just give you a graph G, which is just an adjacency matrix, right, and I ask you to identify the connected components in that, which means which parts belong to one component, which in other. The process is that first you compute the Laplacian, right? Laplacian is just d minus w. Then you do the eigenvector analysis of that Laplacian.
So you have the eigenvector matrix.
Right.
But when you return into the
Oh, so when you do eigenvector analysis, remember you get eigenvectors and eigenvalues.
Oh,
right? So it's
eigenvalue, sum of the eigenvector.
no. For that, I think you would have to maybe go back to a little bit of algebra, right? But I'm going to just quickly tell it here. So if you have any matrix A, right? This is a square matrix, and you multiply it with a vector x, and you say that the solution of this is lambda x. If you're trying to solve this, right? So for this particular system of equations, the solutions would be eigenvectors of A, right? So if you take any eigenvector of A, that will be equal to V times lambda, where lambda is the corresponding eigenvalue, right? So that is the idea. So you use the eigenvalues to identify which eigenvector I want to look at, right? So you basically that the analysis that I showed you earlier says that there will be exactly two disconnected components. If there are two exactly disconnected components, then there will be two zero eigenvectors, so that you can identify like this. And then if you look at the corresponding eigenvectors, then you can identify which nodes belong to which disconnected component, right? So that's the process. Now the next point is that what if the graph is not completely disconnected? What that says, I mean, so the same logic holds there as well, is that if you have a graph which does not have disconnected components, but if it has nearly disconnected components, so for example, if you have a graph like this, right? So there is if you do its eigenvector analysis, then you will not find two non-zero eigenvalues, but you can look at the smallest eigenvalues, all right? If you look at the smallest eigenvalues, that will help you identify the nearly disconnected components. So if I do the eigenvector analysis of this, right? So of course, there will be one zero eigenvalue, right? That is the property of a Laplacian anyway. But that just tells you this gives you the first disconnected component. This is the whole graph itself, right? Because this graph only has one disconnected component. But if you look at the second eigenvalue, right, this one will give you the next disconnected component, all right? So maybe you can run it later, but essentially the idea is that the same analysis will help you identify the nearly disconnected components if you analyze the smallest eigenvalues, all right? So that is the basic idea. All right, so now how does it help us for spectral clustering? Is we've done all of this, right? So this is the thing, right? So if your graph, this is the adjacency matrix of the graph, does not have k isolated connected components, which means disconnected components, you can still analyze the Laplacian, because by perturbation theory, and if you look at the handouts, I think I have a little more about it, the smallest eigenvectors of L will tell you which nodes belong to which component, right? So you could do that. So this is sort of a simple algorithm to do clustering now. So if I have a W, I can compute the first k eigenvectors of L. When I say first, these are ordered ascending order by their eigenvalues, and I construct this new matrix, okay? And then I do k-means clustering on that. So that is how spectral clustering works. So essentially, you are replacing every node's adjacency matrix by its top eigenvectors of the Laplacian, and then you're doing k-means clustering on that. So that's the whole clustering algorithm, and that helps you identify clusters a little better. So this is the output of spectral clustering, right? So remember, k-means clustering gives you this, not good. Spectral clustering gives you this, which is better, right? And I showed this to you last time as well. So this is a short sort of demonstration of how different clustering methods work on different data sets, and this can help you understand what are the strengths and weaknesses of all these methods. Any questions? Yeah. Okay, right. So the NP-hard problem is that if I give you if I give you a graph, right, and I want you to identify k cuts in the graph such that this is optimized, this is maximized or minimized actually, right? Then identifying those k cuts cannot be done using a polynomial algorithm. So that is the question. Right. Uh, I don't think it will give you. It will always. It is guaranteed to give you the exact answer. It will give you answer if there are disconnected components, right? So this problem does not assume that your graph has disconnected components. If your graph has disconnected components, then using that eigenvector approach will give you those components. So that can be done in polynomial time. But if it is not, then you can't. Any other questions? Fantastic. So, okay, so that brings us sort of to the conclusion of the entire syllabus that I wanted to cover. And we have looked at many things, right? So now I'm going to spend the next 12-13 minutes and next class trying to give you an overview that will help you prepare for your exam, right? And of course, it will also help you sort of get a general sense of things that we have done, right? So what I did yesterday was that on Piazza, I posted all the topics that we have sort of discussed after the first exam. So these will be the topics that will be covered for, let me view on Piazza for the exam, right? So this is a general idea. So the point is that the exam will be very much like the midterm, which is it will have only objective questions, right? But if some of you have pointed it out to me as well, is that the nature of the problems that you saw in gradients for second part were kind of different from the first part, in the sense that in the second part you had to do a lot of numerical computation. Sometimes you had to use some code and everything, right? So of course I would not expect you to run code during the exam. You would have to have a scientific calculator, because I think you might have to compute logs of things. So the questions would be slightly different, in the sense it's a little harder for us to come up with questions that are similar to the midterm, but we'll try, right? But the general idea is that when you prepare for the exam, since there are a lot of topics that I have covered and there's a lot of material, I think it might be easier for you to sort of follow this outline and try to understand each one of these sub-concepts. And this is besides practicing all the gradients problems and everything, right? And that will help you. So what I would advise you is that whenever you start preparing for the exam, start from this, right? And see, okay, do I know the answer for this, right? If I don't, you go back to your notes or the handouts or the slides or the video and try to understand where the answers are. And of course you guys can discuss on Piazza and everything, and I can help as well. So the general topics that we would be looking at, now one thing is that we won't be looking at what was that called, the discriminant analysis, the quadratic discriminant. That was in the second assignment, but we won't cover that in this exam, so you can ignore that for that, right? We would also not do too much of you had come to my office hours about linear Gaussian systems, right? So for the exam, let's say we will not cover that, right? So linear Gaussian systems, the reason I sort of talked about them was that gave me an easy way to jump into linear regression. So let's start with linear regression, okay? So linear regression, we looked at it, it's a linear model, right? So there's a notion of how you learn the weights. So the first thing you want to understand is what is linear regression, right? Then you need to understand, okay, how do you learn the weights? What is the notion of a bias term? What does it mean geometrically? There's a line fitting problem that's that corresponds to linear regression, right? We also talked about basis function expansion, which means that if we don't want to fit a line, if we want to fit a curve, right, we can do something called basis function expansion, where you take your data and you expand it using some polynomial expansion or any other function, and then learn a line, right? We also looked at robust regression. So the reason we looked at robust regression was that we first looked at, okay, regression, linear regression, the way it fits, right, is a little biased. It gets affected by outliers, right? So then we looked at one method called robust regression, which lets you accommodate the presence of outliers, and that is known as robust regression. This kind of falls in a general machine learning area of robust learning, right? Learning in the presence of noisy or outlying data. Yeah. Then we looked at some other issues with linear regression, which was more about, it being unstable, not interpretable, and so on. And then we looked at an important concept of regularization, right? So that is a general notion. We have looked at regularization even in the context of neural networks, right? But we looked at regularization. We looked at two regularization models for regression. This is ridge regression and lasso, right? So ridge regression is where you try to minimize the square norm of your weight vector. Lasso is where you try to minimize the L1 norm, right? And they are different, and there is some property of lasso, some property of ridge regression, and we have sort of understood all of them. So you need to understand those. Then we also looked at, okay, how do we solve the optimization problem? So that's just computing the derivative. You have done this for a programming assignment as well. Then we also looked at something called Bayesian regression, right, where we said, okay, instead of treating it as a error minimization problem, let's try to pose it as a likelihood maximization problem, right? So because we are calling it Bayesian, which means that even your weight vector was treated as a random variable. So we put a prior on your weight vector, and the learning means you're trying to get the posterior of the weight vector, right? So we did all of that, and then we also saw how that is connected to ridge regression, right? So because in the prior, we are assuming a Gaussian prior, which means that it translates to sort of ensuring that the norm of your weight vector is not too high. So they're related, all right? And then we also looked at how, in the same vein, how lasso is related to using a Laplace prior. So if you use a Gaussian prior in Bayesian regression, then it becomes very similar to ridge regression. But if you use a Laplace prior, so if you go to your notes, you will see discussion on Laplace distributions, right? So it's just like a normal distribution, but instead of having e power minus x minus mu square, it is just x minus mu L1 norm of that, right? So it kind of looks like lasso. So you need to understand that. Then we looked at a general topic of discriminative classifiers, and we didn't spend too much time on that, but the idea there was that discriminative classifiers are different from classifiers like Gaussian, naive Bayes, or those ones, in the sense that they do not try to learn the generative model directly. So they directly try to understand what is the probability of y equal to 1 given x, and so on, right? So we looked at one of them, which is called logistic regression. Right? And then we saw, okay, logistic regression is actually a classifier, right? Even though it has the word regression in it, it doesn't do regression, it does classification, whereas linear regression does prediction, right? So the difference between logistic, so there are some similarities between logistic and linear. In both cases, you do W transpose X, but in linear, you just use W transpose X as your prediction, whereas in logistic, you apply a sigmoid function on it to squash it between 0 and 1, and then you use that as a probability, right? So you need to understand that as well. Then we looked at this very interesting area of kernel methods, which is that you're trying to apply all of these methods in scenarios where X is not really a vector. So instead of having X represented in a d-dimensional space, we assume that we have some way of computing similarities between data points, and so we call those kernel functions. And then we saw that some of the machine learning methods can still be applied, because all they do is they use an inner product of your data points, which means that if you replace that inner product with any other kernel function, you can still apply those methodologies, right? So we saw how to use linear regression in this setting. And then we also looked at something called the RBF machine. We also looked at RBF kernel, which means that which essentially means that you're taking your data and you're projecting into this infinite dimensional space and trying to do the classification there. So we looked at all of that. And then we moved on to another type of linear classifier, which, yes,
Can you explain a factor check?
to a potential. All right. So we also looked at when would a function be a valid kernel function, right? So a kernel function is essentially a function that takes two data objects and produces some similarity value, right? But it turns out that you cannot just use any function as your kernel function. They have to follow certain property. And the property means is essentially that the kernel matrix that you get should be positive semi-definite, right? So if you design a kernel function, tomorrow if somebody comes to my door and says, here's a new kernel function, the first thing I'll ask that person is this valid, right? And the way that person has to prove it is by proving that if I take any bunch of data points and create a similarity matrix by applying that kernel function to each pair, it should be positive semi-definite, right? And how do you prove that something is positive semi-definite? Is that you have to show that k times x, x transpose k of x for any x, any non-zero x, should be a 0 or larger value, right? Sometimes it's harder to show that, right? So then what we do is we use certain properties. So maybe I go back for D3. No, x, so I mean that's sort of more a mathematical notion, right? To prove that any matrix is positive semi-definite, you have to show that for any vector x, x transpose ax, that will be a scalar value that should always be greater than 0. So somewhere I had that, right? Choosing kernel function, is that where it is? Right, so here we said how do you construct it? It should have this property, right? And so you can either go by first principles and prove that your kernel function will give positive semi-definite gram matrices or kernel matrices, or you can use these properties. So these properties essentially says that if you have a known kernel function, okay, which you know it is a valid kernel function, then any derivative of that kernel function of these forms will also be valid, right? So for example, if I have a kernel function which says kx and xi and xj is just xi plus xj, let's just for example, then a new kernel function which does 2xi plus 2xj will also be a valid kernel function because of this property, and so on, right? So this is where I'm getting at in this question. All right, so then we quickly then we looked at something called maximum margin classification. So that is another form of a linear classifier where you're trying to learn a line, but you're also trying to maintain some other property. In this case, you're trying to ensure that the margin is maximized. And then we also saw why we do that, because it turns out that maximizing the margin in some sense also means you are trying to regularize your solution. So you are avoiding overfitting, all right? And then we looked at a slightly mathematical concept of using Lagrange multiplier methods to solve constraint optimization problems. You don't have to really know this in a very detailed way, but if you can essentially follow the arguments that we had in our lectures, that should be enough. Then there's a notion of what is a margin, what is slack, what is C. So this is all in the context of SVM learning, right? What is the kernel trick, right? So that follows from fourth point, that how can you use kernel functions in SVMs, right? And it turns out that by using the Lagrange the dual optimization formulation, you can use the kernel tricks as well. There's a notion of support vectors, you need to understand that, right? Then we also had one discussion on loss functions and regularizations and so on, right? So you need to understand that as well. So there's a general loss function that we showed, which is essentially that 0-1 loss. And then we said, hey, optimizing over 0-1 loss is not easy because it's not a very nice mathematical function. So we use other loss functions, and that gives us different classification methods like logistic regression, SVM, perceptron. So in essence, they are kind of similar because they all do W transpose X, but they have some difference in the way they learn their the weights, right? Then we looked at k-means clustering, spectral clustering, so you want to understand that. This is essentially what we did today. So you can, but I folded it into that discussion. Then we looked at a general area of latent variable models, right? And in that we looked at these 4 different things. So mixture models, we looked at an algorithm to learn the parameters of a mixture model. So that is EM, or expectation maximization. We looked at another latent variable model called factor analysis. Then we saw that principal component analysis looks like a special form of factor analysis. Then we looked at SVD, which is one way of doing PCA, but then we looked at other properties of SVD as well. In particular, we saw how SVD can be used for recommender systems and for image compression as well, right? So go through this list and then sort of track this in the lecture notes and videos and so on. Any questions, you can post it on Piazza or just shoot me an email. All right, any questions so far?